Hello all, my name is Ashutosh Rastogi. I am a teacher by profession. My mission is to impart quality education for all. For that purpose I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, in this particular lecture, we will try to discuss about various generation and detection methods of single sideband suppressed carrier signals. These are the outlines. We'll start up with the introduction. Where we will give a brief overview what we have learned so far. Then there are basically two methods for SSB signal generation. They are filter method and phase method. We will discuss one by one. And then finally we're going to conclude with demodulation of double sideband suppressed carrier systems. So in the last lecture we have studied about the basics of single sideband systems, its mathematical details and its spectrum. We have devised up the facts that SSB-SC signals are one of the most bandwidth efficient as well as power efficient systems. We have also seen some introduction about the Hilbert transform and we have discussed some of its properties. Now in this particular lecture we are going to discuss how we will going to generate one of the most power as well as bandwidth efficient scheme. So there are broadly two methods for generating the SSB-SC signal. They are frequency discriminators and the phase discriminators. So in frequency discriminator, we will basically generate SSB-SC signal from the double sideband suppressed carrier signals by using a specific band pass filter. Specific means although it is band pass filter, but its quality factor is quite higher. And in phase discriminator, we basically generate the single sideband suppressed carrier signals via using the Hilbert transform. So here is the block diagram of filter method. We'll be having a balance modulator where we will going to apply a carrier signal, and via microphone we are basically producing a speech signal via some audio amplifier. So at balance modulator we have two inputs. Number one is carrier signal and second one is the message signal. So balance modulator will going to generate a double sideband signal as we have already discussed in our DSP-SC signal generation. Then that signal will going to pass through a sideband filter. Since we know that in double sideband systems we have one upper sideband and one lower sideband. So the role of sideband filter is it has to be precisely select any one sideband, either upper sideband or the lower sideband, and it will going to pass it through the amplifier. Since sideband filter is precisely selecting only one sideband, so at the output you will be only having single sideband, that is either upper sideband and lower sideband, and this signal will get passed through a linear power amplifier, and after that we're going to forward it to the antenna for further RF signal transmission. So by this manner we will going to generate our single sideband signals. If we closely observe that, it is our double sideband suppressed carrier system generation method that we had already studied. So now we will going to understand the working of the filter method in greater detail. So in filter method, it is one of the most simplest method and most widely used method for generating the single sideband signals. As we had already mentioned that modulating signal or message signal has been applied to the audio amplifier, and then the amplifier's output is fed as the one of the input to the balance modulator. Obviously we know that the second input of the balance modulator will be the carrier signal. So for having or generating our carrier signals, we are using some crystal oscillator since it provides the stable carrier signal. The output of the balance modulator is the double sideband suppressed carrier signals, and this double sideband suppressed carrier signals would have been passed through a highly selective band pass filter, which will going to precisely pass only one sideband, that is either upper sideband or lower sideband. So by this manner we will going to have only single sideband system, that is upper sideband suppressed carrier systems or lower sideband suppressed carrier systems. In our example we are selecting upper sideband. So with this filter method, it is necessary to select either the upper sideband or lower sideband as we have already discussed. So depending upon whether we are picking up the upper sideband or lower sideband, we will be having two variants of SSB-SC signal, that is upper sideband SSB signal or lower sideband SSB signal, as we have discussed in our last lecture. So now we're going to discuss some of the problems associated with the filter method. Since it is very difficult to form such a filter which can pass only one sideband, I mean we are talking about highly precise filter which is having a very sharp cutoff, which is having some high selectivity. So some of the problems are, obviously we need some high quality factor filters which have very sharp cutoff in order to get the complete sideband. So quality factor has been defined as it is the ratio of FC over bandwidth, where FC is the carrier frequency or critical frequency or cutoff frequency. You can name it. Since quality factor is the ratio of FC to the bandwidth, so we can conclude that if bandwidth is lower, then the ratio of FC over bandwidth will be higher. It means we're going to have some high quality factor. So in practice, we can say that the inductor and capacitor, nothing are ideal. They obviously having associated certain losses in them in terms of resistance, or we could say energy dissipations. So hence it is very hard to construct such filters. I mean, if we're talking about some ideal components such as inductance and capacitance, then we could say that there is no leakage and we are having certain ideal characteristics, or we could say that our signal will not going to lose anywhere. But since they are lossy component, so obviously it is very hard to construct such ideal filters which can have such a sharp cutoff frequencies. So now second method for generating the SSB-SC signal is the phasing method. So this particular figure shows the block structure, how we will going to generate the SSB-SC signal with the help of phasing method. So construction wise, if we talk about, it contains basically two modulators. This is our balance modulator 1 and this is our balance modulator 2. So the input to the balance modulator is, one input is our message signal or modulating signal which has been given as AM cos of 2 pi FMT, and the second input to this balance modulator is AC times of cos of 2 pi FCT. Basically, we are applying the same carrier frequency to both of the balance modulator, but the second balance modulator is having the same frequency but with 90-degree phase shifter. So basically, if we closely observe, balance modulator 1 is having the input message signal AM cos of 2 pi FMT, and second input as a carrier is AC times of cos of 2 pi FCT. Whereas in the second balance modulator, we will be having a message signal which is out of phase by 90-degree, and the second input to the balance modulator 2 is the same common carrier frequency, but it is also 90-degree phase apart. So what we're going to do is we will going to perform a summation operation to the output of both these balanced modulators, and at the output of the summer we will be having a SSB-SC signal. So how we're going to do it? Basically, so at the summer, what we'll be having? We'll be having V1T and V2T. When we're going to add up, so since we are having 90-degree phase apart carrier and the signal, so one of the sidebands will get cancelled as the phasing. So we will going to understand this via some mathematical detailing in our upcoming slides. So the phasing method of SSB-SC generation uses phase shift technique that causes one of the sidebands to be cancelled out. So how this actually being happening, we will going to understand it via some mathematical details. So the phasing method uses two balance modulator which eliminates the carrier that we have already seen in the block diagram description. The carrier oscillator is applied to the upper balance modulator along with the modulating signal that we have already discussed. The output of the balance modulator 1, that is V1T, would have been calculated as V1T is equal to AM times of cos of 2 pi FMT multiplied with AC times of 2 pi FCT. This is basically our carrier signal and this is our message signal. So we did nothing but we just have tried to apply 2 cos A cos B formula on this particular equation So we are left with AC times of AM upon 2, that will get multiplied with 2 times of cos of 2 pi FMT cos of 2 pi FCT. So after applying 2 cos A cos B formula, what we are left with is cos of 2 pi FC plus FMT and cos of 2 pi FC minus FMT. And the amplitude of this combined signal is AM times of AC by 2. So this basically represents upper sideband and this represents lower sideband. So again, this is the double sideband suppressed carrier signals. As we already know that the output of any balanced modulator is a double sideband suppressed carrier signal. So the carrier and the modulating signal both are shifted by 90 degrees and applied to the another balanced modulator, that is balanced modulator 2. So what will be the output of balanced modulator 2 is, let us again understand it with some equations. So the output of second balanced modulator is V2T, which has been given as AM times of cos of 2 pi FMT minus 90 degrees, since we are applying 90 degree phase apart to the original message signal, and it will get multiplied with AC times of cos of 2 pi FCT minus 90 degree, which is also 90 degree phase apart. So we know that cos of 90 minus theta is equal to sin theta. So we have applied simple trigonometric formula over there. So we are having AM times of sine of 2 pi FMT multiplied with AC times of sine of 2 pi FCT. This is again a variant of double sideband suppressed carrier signals. So what we're going to do that next, we're going to apply 2 sin A sin B formula in this particular equation. So we are left with AM times of AC by 2 multiplied with 2 sine of 2 pi FMT with the sine of 2 pi FCT. So now again we'll be having cos of 2 pi FC minus FMT minus times of cos of 2 pi FC plus FMT. This is our upper sideband and this is our lower sideband. But if we closely observe that here will be upper sideband with this minus sign, and when we're going to add up with the signal V1T, they both will going to cancel out with each other and we are only left with lower sideband signals. So phase shifting causes one of the sideband to be cancelled out when the two modulator outputs are added together. This is what I have tried to explain you. So the output of the summer turns out to be, since at summer both of the signals V1T and V2T, that is the outcome of balanced modulator 1 and balanced modulator 2, will get added up and we'll be having ST is equal to AM times of AC by 2 multiplied with cos of 2 pi FC plus FMT plus cos of 2 pi FC minus FMT added up with V2T, that is AM times of AC by 2 cos of 2 pi FC minus FMT minus cos of 2 pi FC plus FMT. So this minus sign of upper sideband and this positive sign of upper sideband, both these upper sideband will going to cancel out to each other, and what we are left with, AM times of AC cos of 2 pi FC minus FMT. So this is the equation of our SSB-SC signal, which contains lower sideband signal. So this is how we will going to generate our SSB-SC signal. Now we will going to focus or discuss how we will going to detect or demodulate our SSB-SC signal. We can demodulate SSB signal via simple product detector and passing it through a low pass filter. So what we're going to do is, a product detector is a balanced modulator or detector that is used to receive or recover the message signal. So any balanced modulator can be used as a product detector to demodulate the SSB-SC signal. So what we will again going to do is, we will going to apply our modulated signal ST with the same carrier signal that has been used at the transmitting side. We will going to apply them together, and after passing through the low pass filter, we will going to get the message signal MT back. So after passing the output of the product detector through low pass filter, we get the message signal. This is what I have explained. So this is the block diagram of our SSB-SC signal demodulator. We are going to apply SSB signal to the balance modulator, and second input is the carrier oscillator. Again, we are using the same carrier signal that has been used at the transmitting side or at the time of generation. So when we're going to pass it through the low pass filter, we will going to recover our message signal back. Let us understand it with a small numerical example. Suppose at the input side we'll be having SSB signal which is having upper sideband and frequency it is carrying is 1003 kilohertz. Second input to the balance modulator is the carrier signal whose frequency is being 1000 kilohertz. So when we're going to apply these two frequency component at the balance modulator, what we're going to have is we'll be having one with the plus sign that we call it as a upper sideband and one with the negative sign that is called lower sideband. So one frequency it will be at 2003 kilohertz and second is 3 kilohertz. So when we will going to pass this signal through a low pass filter which is centered around audio frequencies, we will only going to recover this 3 kilohertz intelligent message signal and it will simply going to reject the 2003 kilohertz or higher side of signal. This is how we are going to generate our SSB-SC signal. These are the references. Thank you very much for your patient hearing.